Today's class is a crash course in machine learning. We'll take a look at simple examples. Before we start talking about machine learning, we can talk about learning itself. When you think of the word learning, what are some things that you think of? There are many examples. For instance, you can learn to play instruments. You can also learn to speak a language. And perhaps you can learn to not touch something hot. Here are some definitions proposed by computer scientists. Arthur Samuel said, "Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed." Tom Mitchell said, "A computer program is set to learn from experience E with respect to some class of tasks T and performance measure P if its performance improves." The key thing here is the experience with respect to some task measured by P. Like many things in artificial intelligence, these definitions are subjective, so you may or may not agree with the idea that you have to be able to measure something, otherwise it's not considered learning. And here are some examples of TEP configuration. If you consider spam filtering, the task is to classify emails as spam or not spam. The experience you need would be a bunch of emails labeled as spam or not spam. Your performance measure can be the probability of error on new emails. And we'll revisit how we estimate this probability. Another example could be information retrieval, like search engines. So there, the task is finding documents relevant for a query. The type of experience you need would be the user interaction with a search engine, like Google. You're observing what users type in as queries, and then which link they're clicking. And you can measure the performance as the number of relevant documents in the top 10 links that the search engine displays. And for chess, the task could be to play chess to win. And then the experience could be you can have the chess program play against itself. And then the performance would be percentage of wins. The idea of learning from data can be summarized as follows. First, we have some functionality F that we're interested in. For example, we want to be able to tell whether the given image is an image of a cat or not. The thing here is that we don't want to implement F ourselves. But instead, we want to set up a program that can take a look at examples or experiences and approximate a function h that's as close to f as possible. So for example, in the supervised learning setting, each image, say x1 and x2, comes with a true label or class, f of x1 or f of x2. So if x1 is an image of a cat, f of x1 could be true, denoting that it's a cat. And if x2 were not an image of a cat, f of x2 could have been false. So each image comes with the true class. Obviously, we don't have f, but we just have the output of f. So in other words, we know whether an image is an image of a cat, though we don't know exactly how to tell apart cat images from other images. In the case of unsupervised learning, you just have data without the labels or classes. So basically, imagine having a bunch of images without knowing whether it's an image of a cat or a dog. Then how do you expect the program to learn how to distinguish cats from others? Well, in this case, the program ends up clustering the data. Ideally, it will group all cat images as one group and everything else as another group. Basically, the program is learning to group cat images and group non-cat images without knowing that which group is actually the group of a cat, using the similarity of pictures. And semi-supervised falls in between supervised and unsupervised learning, where only a part of your data comes with the correct label or class. And lastly, you have reinforcement learning that we have seen before, where instead of starting with a whole set of examples, you have the agent perform actions and you specify rewards and punishments. And as the agent seeks to maximize rewards while minimizing the punishments, it will become better at the tasks that we're interested in. One important underlying assumption is that the data we have to train our programs has to be a good representative of the true population. If this is not the case, then the program we train using this dataset may not be usable in real world. For example, suppose in our dataset of cat and non-cat images, all our cats have black fur and all non-cat animals have white fur. Then our program may be trained to classify things as cat as long as the fur is black, which is totally not true in real life. When we just discussed supervised learning, we talked about how each data comes with a label or class. And when you have a finite set of classes, it's called classification. And when you have an infinite set of classes, it's called regression. Given a high-level task, you can frame it as a classification task or a regression task. For example, suppose we're trying to program an autonomous vehicle. We want the program to be able to tell if it should go straight or make a turn or so on based on the image that it sees from the windshield. So the classification approach would be saying, okay, there are only 3 options. You can go straight, go left, or go right. So that would be an example of classification. Or you can frame it as a regression problem. Turn the steering wheel so that would be a regression problem. For medical diagnosis, in the simplest case, you can say sick versus healthy. Again, that would be a classification problem. And if you frame it as the probability of being sick, that would be a regression problem. And again, for stock market prediction, it could be up, down, or it could be plus or minus X%, which would be a regression problem. If you frame a high-level problem as a classification problem, then it's easier to get the data, and you'll have an easier time scoring high according to the performance measure you have. But it may not be as useful in practice. So often what happens is when a new task, when researchers design So often what happens is when a researcher defines a new novel task, when a researcher defines a novel task, they start off with classifications, say true or false. And then so here's an overview of supervised learning again. So here's an overview of supervised learning. So here's a visual overview of supervised learning. So we have some training. So we start with some training data, and then we feed it through some learning algorithm. And the output of the learning algorithm is what's called a model or classifier. And once you have this classifier, you use that classifier to test. You use this classifier to classify an unseen data and see what it classifies and have it output the class. Here's a visual summary of the supervised learning. So here's a visual overview of supervised learning. So you start with some training data, or the data you use to train your model or classifier, and you feed it through some learning algorithm, because there are different ways to learn from data. So the learning algorithm outputs a model or classifier that hopefully does what you want it to do. Once you have this classifier, then we can try fitting in some data that we didn't use for training, and it should output a class, and hopefully it's the correct class. For example, suppose we're trying to build a classifier that can distinguish male from female pictures. So we have some training data, we feed that into some learning algorithm, and then it outputs a model or classifier. And then we give it an unseen image, and hopefully it will output the correct class. So let's look at the first learning algorithm called decision tree. Let's consider an example. Suppose we're interested in learning how Trump decides whether he should leave a big tip or not at a given restaurant. We don't get to ask him how he makes a decision, and maybe he doesn't even know himself, but we have this data to work with. So he's been to 4 restaurants, where for 2 of those he left big tip, and for the other 2 he didn't. And for each of these restaurants, we have some information like, is the food great, is the service speedy, is the price high or adequate, and so on and so forth. Suppose that we know Trump went to a new restaurant where the food is good, he was not able to have a good chat, the service was speedy, the price was high, there was no bar. Would he leave a big tip? Yes or no? To organize our thoughts, we can first consider the first attribute, food. And for the attribute food, there are 3 possible cases: great, mediocre, and yikes. And we know that for the restaurants in our data set, restaurants 1, 2, and 4 had good food or great food. Restaurant 3 had mediocre food. And then there aren't any restaurants in our data set which has yikes for food. When it comes to restaurants 1, 2, and 4, no, yes, yes. So we have a mixture of yes and no. And then for restaurant 3, it was no. So we have no. And yikes, we don't have any data. But let's suppose that we decided no to be the default class. Which was an arbitrary decision. And then we'll consider the next attribute is the service speedy. So of the 3 restaurants that had great food, 4 was the only place with speedy service, and they did get big tip. And the other 2, restaurants 1 and 2, the service wasn't speedy. So we continue on and use the attribute price to distinguish the restaurants, and it turns out that restaurant 2 had an adequate price and did get a big tip, and restaurant 1 had a high price and did not get a big tip. So using this data, we built a tree that we can use to make decisions. And when we have a new restaurant, we can use this tree to decide whether Trump would leave a big tip or not. So the new restaurant we're considering had great food, no for chat, yes for speedy, high for price, and no for bar. So food, it was great. Speedy, it was yes. So we would assume that Trump left a big tip at the restaurant. And what we just looked at is a very simple example, but you can imagine how complicated it could be with lots of attributes and lots of examples. In the previous example, we built the decision tree manually. So now we'll take a look at how we can build decision tree automatically from the data. So there's this concept called Occam's razor, which says you should prefer what's simpler as long as they function the same. And in the case of decision tree, we should prefer decision tree with the fewest number of nodes as long as it performs the same as other more complicated trees. The problem with that is building the smallest tree is computationally hard. So instead, we're going to resort to finding some small tree which may not be the smallest tree using a greedy algorithm. And it involves the concept of entropy. Suppose we have a dataset with 12 examples. And if we use the attribute type as a root, we get this division. Whereas if we use patrons, then you get this division. Should we use type or patrons as a root of our decision tree? So we definitely prefer patrons. Because using Patronus alone, we're able to correctly classify 6 of our data points. So in the future, for some new restaurant, if we look at the Patronus attribute, and if it's none, we can classify that as no, and if it's some, then we can classify it as yes, big tip. If it's full, we don't know yet. We need to consider more attributes. But as long as the new restaurant has none or some Patronus, we'll know how to classify it. On the other hand, if you consider type, whether it's French, Italian, Thai, or burger, we won't know how to classify the new restaurant. This intuition is captured by the concept of entropy. As you can see, the uncertainty is high when type is used. In this case, we also say the entropy is high. When we use Patronus, then the uncertainty is lower, and we say the entropy is also low. Again, entropy is the measure of uncertainty, so if it's more uncertain, then the entropy is bigger. And this is how you compute entropy. And here, v1 through vk are the values the random variable v can take on. For example, let's consider a random variable with 2 values, heads or tails, and suppose it's a fair coin. So you have 50% chance of getting head and 50% chance of getting tail. And suppose we have another coin, but now it's loaded coin. So we have 99% chance of getting head. And 1% chance of getting tail. So obviously, the first case is much more uncertain. So the first case is much more uncertain, and it's captured by this value. And if you had a fully biased coin with 100% chance of getting heads every time, then it would just be -1 log 1 minus 0 log 0 equals 0, which is the smallest entropy possible. So there's no uncertainty, so you have 0 entropy. So at this point, hopefully you're convinced that this weird equation somehow is consistent with your understanding of entropy. So h of f is higher than h of l, and when there's no uncertainty, you have 0 entropy. But you might wonder, how does this actually capture our intuition? Well, so log graph looks like this. Yes, that's 1. So log of 1 is 0, and then as it gets close to 0, then you get a very small number. So negative log would be flipping that over. And note that we're only looking at percentages. This value is between 0 and 1. So negative log of some percentage would be this graph. So this value is small when the probability is big, and this value is small when obviously the probability is small. So this whole expression becomes small when either the probability is close to 0 or close to 1. And to get the biggest value, you need something like this, where the probability falls like right in the middle. So both the probability and log of the probability are big enough. That's the only case where you have a big entropy.